In transistor, we have two types of configuration. One is the common base configuration, the other one is common emitter configuration. This is the diagram for the common base configuration. This is the transistor in which we have these two voltages provided to these three terminals of this transistor. These voltages are provided in such a way that here this base is taken as a constant between these two voltage, and therefore we call this arrangement as a common base configuration. Okay. So this is the circuit diagram for that common base configuration. We have that same voltage, and the voltage which is connected between the emitter and the base, we call that as VBE. The other voltage which is connected between this C, the collector, and the base B, we call that voltage as VCB. We will connect this voltage in such a way that here this junction, this emitter base junction will be the forward bias, and this collector base junction will be the reverse bias. Here we this diagram, this symbol is actually represent the NPN transistor, because here from this base this line is actually towards this emitter. And as I have discussed in the previous lecture, that if this arrow is towards the emitter, that will represent us that in the base we have the p-type semiconductor material. Okay, so this is the same diagram as of this, but here this is the symbolic representation. This is the circuit diagram for this arrangement. Okay. So if we have two types of the characteristics. One is the input characteristics for the common base configuration. The other one is the output characteristics for the common base configuration. And if we perform that, the graph will be on the basis of the experiment we perform on the transistor. The experimental graph will give by this common base configuration, and that will look like this. This is for the input characteristics for the common base configuration. This is the experimental graph for that. Okay, so for the input characteristics, we will take this VBC, okay, VCB, this voltage as a common. Okay, we will bring changes in this IE, the emitter current, okay, with respect to this voltage VBE at constant VCB, and we will collect the data from this, and experimentally if we draw that, it will give us such like a graph. Okay, and this graph is called the input characteristics. Okay, again I'm going to repeat this. In this input characteristics, we will bring variation in the emitter current, i.e. variation in the emitter current, i.e. with respect to this VBE at constant VBC. Okay, at constant VBC. Then again we will take other constant VBC, which is 8 volt. Then we will take the other constant as VBC as 18 volt. Okay, and we will see what is the variation for the current IE at by changing the voltage VBE at constant VBC. Okay, so here again I'm going to repeat that. Here the current is contributed by these two voltages. Okay, in order to take the experimental data from this, and in order to make the diagram, the graph for this, in graph here in this graph, only two things will be compared. Okay, so here on the x-axis we taken only VBE, and on y-axis we taking IE quantity. Okay, so For that, in order to have two quantities, and we are going to analyze the variation in that two quantities, we will take the other quantity as a constant. Okay, so therefore we taken this VCB as a constant, and we are going to change this IE. Okay, this IE by changing this VBE. Okay, so if we change this VBE, the IE will be changes. Okay, and this is the graph for that, and we will take this VCB as a constant, and this graph is called the input characteristics. Okay, this graph is called the input characteristics. So, as we discuss that this VBE is the forward bias, this VCB is the reverse bias. Okay, so if we taken this VCB as a constant, okay, there will be no variation in this transistor due to this VCB that is constant, that has the constant value. Okay, so if we change this VBE, this voltage, the current will be induced. Okay, if we change here, this VBE is actually connected between this emitter and this base. If we change its value, its magnitude, here the current will be changed, because here this is the forward bias. If we increase that voltage, okay, here we have the potential barrier, in PN junction we have the potential barrier. There is the electric field inside that junction, in the PN junction, they do not allow the electron to move from this N-type material to P-type material. Okay, and still, as we know, for the silicon it is about 0.7 electron volt. This potential barrier is about 0.7 electron volt. So up to 0.7, if we increase this VBE up to 0.7, there will be no current, because up to 0.7 still this junction will do not allow the charges to flow from this junction. Okay, what I'm going to say here is that let's say if we have the silicon, and on top of which we grow these on top of which we grow another material as boron or phosphorus, and we make such like transistor. Okay, so the parent element here is the silicon. Okay, so for the silicon, the voltage, the potential barrier is the 0.7. So here we have that same potential barrier, which is 0.7 electron volt. Okay, so if we provide this VBE, which is less than 0.7, let's say that is 0.3, then there the electrons from this N-type material will not jump to the P-type material due to that potential barrier, because this voltage do not exceed that potential barrier. That potential barrier is actually 0.7 electron volt, and we provide here a 0.3 electron volt. If we increase its value up to 0.5, then here this potential barrier will be less. Okay, and if we increase this further up to 0.6, this potential barrier will become less, and some of the electron will start jumping, and here a minor current will be up here. Okay, and here this graph is going towards upward. Okay, and some minor current is will be up here when this voltage is up to 0.6. Okay, if it approach to 0.7, the current will be increasing, and if it exceed the 0.7 voltage, which is actually the voltage, the PN junction voltage, the potential barrier voltage, if this external VBE voltage exceed that potential barrier, then suddenly this potential barrier will be vanish. There will be no potential barrier. All electron will be pass from this region, and here it behave as a conductor, and such type this type will be here the current will be suddenly increased. There will be no resistance, and in this case the transistor will behave as a conductor. Okay, Now again we have that same case. Okay, we have that same case, but here we have increased this potential, this VCB up to 8 volt. Okay, still we taken that as a constant at 8 volt, and we do not change this voltage, but again we are going to change this VBE, due to which this potential barrier will be decreasing, and still suddenly the current will be start, and in that case we will have this value, we will have this graph. Okay, and again for 18 volt, if we take the VBC as 18 volt, and if we change this VBE, the current will be changed, and that behavior is given by this graph. This graph give us that behavior. Almost all have the potential barrier is 0.7, because that is almost constant for the silicon, which is 0.7 for silicon volt, and silicon, and for germanium, that is about 0.3 electron volt, and for uri semiconductor there will have some that voltage. Okay, that is actually potential barrier made by that here in this is this PN junction. Okay, so this is the input characteristic. So the variation in the emitter current with respect to the change in emitter voltage VBE at constant VBC, we take in VBC as a constant. First we take is 0 volt, then we take is 8 volt, then 18 volt. Okay, and this is the graph for that as a input characteristics graph. Okay, now what is the output characteristics for this common base configuration of the transistor? So for that, we are going to take this IE, the current IE as constant. Now we are going to take this IE as constant. Okay, and we are going to, sorry, in this case, we taken this IE as constant. Okay, and we are going to give variation, to take variation in this IC by changing this voltage VCB. Okay, this arrangement, this changes will give this changes will on the basis of experiment, it will give us some data, and if we plot that data, it will give us some such like graph. Okay, and here we will discuss that which information give us by this graph. Okay, so again, what is output characteristic? Output characteristic is actually the experimental setup in order to take the output from this transistor by taking the IE as constant, and we are going to change this IC by changing this VCB. Okay, so we will take this IE as a constant, we will change this VCB, due to which the change will be occur in the IC, and we will collect that data, and if we plot that, it will give us such like a graph. Okay, this graph is called the output characteristics of the transistor. Okay, so what will happen if we take that as a constant here, IE, if we take this IE as a constant, and now we are going to change this VCB. Okay, so as we have discussed in the previous lecture, that the current IE, if the current IE will be start. Okay, and that current will be, if we have 100% electron, the 1% of the electron, the current, the 1% of the current will be IB, and the 99% of the current will be IC. Okay, the 99% of the current will be IC. Therefore, IE is equal to IB plus IC. Okay, so as again, out of 100 percent, out of 100%, about 99% uh, is the IC. Okay, 99% current is the IC. Okay, in this case, only 1% is the IB. Okay, so therefore, this IE is approximately equal to IC. Okay, so if we take the IE is constant, and V, as I have discussed, this IE is approximately equal to IC. Okay, so here this IC will be approximately equal to that IE. Here I consider this IE is 1 milliampere. That will be approximately equal to 1 milliampere as IC. Okay, and if we increase this reverse bias, there will be no such a variation occur in this area. Okay, this is because of that reverse biasing, this uh, this collector base junction reverse biasing. Okay, now what will happen if we reverse this voltage? Okay, so I from I up in this side of the zero, the polarity will be different. If we change the polarity, this side become the negative and this will become the positive. In that case, this PN junction will be the forward bias, and due to which the current will be occur. Okay, so therefore, from this side of the zero, this graph will be not such as a constant, because here this will become the forward bias, and some minor changes, some the current will be flow in this region. Okay, this will be not constant as IE is equal to IC. So that IC will be not constant, because here this is also become the forward bias. As I have discussed, this VBE is the forward bias. Okay, here this VCB was the reverse bias. Okay, so if we take this always as a forward bias, and here we have the forward bias, okay, then the electron will become from the N to P. Similarly, if this is also the forward bias, the electron will become from this N to P. Some minor current will be occur. So here, due to these electrons, the current will be again stopped here in this saturation region. The current will be stopped. This is because of that the current is also flowing from this region towards the base. The current is also going from this emitter towards the base. There will this current will not flow, because that is this that electrons is not flow, because both are in opposite direction to each other here. So this graph actually give us that information, and this region is called the saturation region in the graph. So in this graph, we from the experiment, we take such type of the graph, and in this graph, this region is called here, where the IE and the IC is approximately the same, and in this region, which is called the active region, this region is called the active region. This is that region when one is the forward bias, this VBE is the forward, this sorry, this PN junction, this junction, this emitter to base junction is the forward bias, and if and similarly, if we have this base to collector junction is reverse bias, then this region of the graph will be from, and this region is called the active region. In the active region, we have the emitter to base junction is the forward bias, and the base to collector junction is a reverse bias. Now in this region, as I have discussed, if we change the polarity of this, then this will be forward, and similarly that will also be the forward region, and we will take this graph, this portion of the graph, and this region is called the saturated region, because here in the saturated region, this the collector, the emitter to base junction will be forward bias, and similarly the collector to base junction will also be the forward bias. Now what is the cutoff region? Cutoff region is actually represent us, give us the information that in which we have this voltage. Let's say if we have this base to collector junction is the reverse bias, and similarly we have this emitter to base junction also reverse bias. In that case, it will give us this region, which is called the cutoff region. Okay, so this was that. So in the active region, as I have discussed, the base to emitter junction will be forward bias, and the collector to base junction will be reverse bias. The collector to base junction will be reverse bias, and the emitter to base junction will be the forward bias. And this region of the graph we call as the active region. In the cutoff region, the base to emitter junction will be reverse bias, and similarly we have the collector to base junction also a reverse bias. And this, in that case, we will take this portion of the graph, and this portion of the graph is called the cutoff region of that graph. We have, on the other hand, the saturated region. In the saturated region of the graph, we will have this base to emitter junction as forward bias, and similarly this collector to base junction also a forward bias. Okay, in that situation we will take this region of the graph, and this region of the graph is called the saturation region. Okay, now we have the common emitter configuration. In the common emitter configuration, we will take emitter as a common between these two voltage. So if we provide, in this case, we will have the emitter as a constant. In the previous case, we have voltage as a constant. In this case, we will have the emitter as a constant. Okay, between these two voltages. So therefore, between these two terminals. So here, if we provide the voltage, which is actually VBE, this is actually BE, because this voltage is connected between this B and this E, this base and this emitter. Okay, and this is connected in such a way that here this is the forward bias, because this positive is connected to the p-type material, p-type semiconductor material. This negative is connected to the n-type semiconductor material, and we call this sort of the biasing is forward biasing. And similarly, we will connect the voltage as VCE in such a way that it will be the reverse bias, because here this VCE is connected between this collector and this emitter, and we will connect this in such a way that it make the reversing. Okay, so in reverse bias we will put the positive terminal to the n-type semiconductor material, the negative terminal of that voltage with the n-type, sorry, that will be connected with the p-type semiconductor material. Okay, but in this case we take an emitter as a constant, but in that case we have taken as a base as a constant. Okay, so here this VBE, this region, this base to emitter junction is the forward bias, and this collector to base junction is the reversed bias. That is actually the reversed bias. Okay, so this configuration, configuration is called the common emitter configuration in the transistor. Okay, this is the circuit diagram for that. Here we have their same diagram, but actually this is the symbol for the transistor, and in the transistor only we have this collector. This is actually, this wing is also represent the emitter, which is common between these two, and we will give input into base, okay, emitter, and the output will be the collector and emitter here. Okay, so this represent the NPN transistor, and this is the same circuit as that of the as we discussed here. Okay, Now, if we give the input signal, it will give us the output signal. And if we perform the experiment and date, and if we collect the data from this, it will give us the graph that also the input characteristic graph, and it also give us the output characteristic graph. Okay. In the KPK book, they do not discuss that. So therefore, I have ignored that in my this lecture. Okay. Now, what is alpha factor? Alpha factor is actually the ratio of IC to IE. This ratio is called the alpha factor. This, if we divide this IC by IE, that will be the alpha factor. The current gain for the collector to be sorry the it is the current gain in this case. So if we divide that IC by IE, that is called the alpha factor for this configuration. Okay. Now, what is the alpha factor? As I have discussed, the ratio of IC to IE. Alpha factor is equal to IC divided by IE. Okay. Now, this IE is approximately equal to IC, as I have discussed that the about 100% only 99 percent only 1% will be the base current, and the remaining will be the collector current. So therefore, IE approximately equal to IC. If that is equal to that, then the alpha factor will be 1, because if these are constant, then they will be if they become equal, then they will be cancelled, and the alpha factor will be 1 for this circuit. Now, what is beta factor? Which is actually the ratio of the IC to IB. Okay. uh, and we also call this as amplification factor in the common emitter configuration, and that alpha factor was for the common base configuration. That was the current gain for the common base configuration, and here this beta factor is actually the amplification factor in the common emitter configuration. So what is the beta factor? As I have discussed, this is actually the ratio of IC to IB, and we know that IE is equal to IB plus IC. Okay. So from here, if we find the IB, which will be equal to IE minus this IC, so instead of this IB, I have put that IE minus IC. Now if we divide IE on top on this nominator and also on this denominator, so it will give, so on the top we divide that IC by IE. Similarly, we divide this by IE. Similarly, we divide this by IE. So this IC by IE is equal to alpha. This is equal to alpha divided by this is equal to 1, because IE divided by IE is equal to 1 minus IC divided by IE again is equal to the alpha. So it will, the beta factor will be equal to alpha divided by 1 minus alpha. That will be the beta factor. Okay, this is actually the current amplification factor in the common emitter configuration. So this was the explanation for the configuration in the transistor.